I'm an architect with IBM Analytics Platform. So today we'll spend some time on Spark streaming. So before we get started, maybe like how many of you already know or work on Spark on a regular basis? So we know our audience when we talk. How many of you are on streaming already doing work? Okay. So this is the fourth meetup that IBM is doing on Spark. So regularly we started with like core, RDDs, data frames, then we were in streaming. So first we thought about we will go library by library. Then we thought maybe we'll change the approach a little bit. Wanted to get your views on that. So Spark streaming is one of the very big topics. So, and I think we got a lot of feedback from the last meetup that, how many of you are regular to this meetup? Have attended this meetup before? Okay. So I think a lot of times we got the feedback that more than 1.5 hours, we don't want to run the meetup. So this session we will do today, Spark streaming is about concepts, architecture, everything about the architecture part of it is the first half. The second half, Sachin will walk through on the code. You'll get some hang of the code today, but we want to do one more session in Spark streaming, which is very specific about how do you do performance tuning, because most of the time if you see in the industry, you can get started with Spark streaming. The real problem you'll see is how do I scale, how do I fine tune my memory, how do I do my performance, throughput, how do I increase? These are the real problems you'll see in the industry. So we don't want to both do together, then it will go like more than 2.5 hours. So we will do one, the next session is exclusively for what problems you face when you do day-to-day operations. And then we originally published that we'll do machine learning as a second one. But now we are thinking we'll change few things and see what all you face problems in Spark as part of your job, every day in industry. For example, interactive analytics, leave apart Spark shell, but when you're doing interactive analytics from a UI perspective with a 3-tier architecture, it's not easy, it's quite complicated. So that we will explain in one session where really these are the problems you solve, how is we are approaching the problem. That way we can brainstorm and get better ideas. And then we wanted to do some amount of, there are different authentication models exist in Hadoop world today. Apache Knox, Hortonworks is pushing, Sentry, Cloudera is pushing, Authorization Ranger is pushing. So we want to have one session exclusive on different authentication and authorization models that exist in the industry and when to use which tool. Like these type of things which we want to do instead of going about, okay, pick up ML, GraphX, like each and every module, because then it will be more theory. You may not be able to connect to what you're doing in the world. Exactly. So most of the things will be like that. So let's get started. Spark streaming is very high throughput, scalable, and a fault tolerant system. So we'll go on each of these words, what do we mean in depth as part of the session itself. So before we get started, what are the features of Spark streaming which are very, very important? How it differentiates from any other streaming application. The first is high-level APIs. So whenever you're doing any streaming application, the most important thing is you need to have a rich set of APIs where you're able to do different operations. For example, as part of the streaming operation, you might have to do lookup on some of the metadata stuff or dimension table, static data set. You need to have a join feature that will be available. And then I'm just going to point a few examples, not go into every detail of it. The second one is streaming application, you always want to do some operation on a window basis. For example, Twitter feed you're analyzing. You should have the capability to say, okay, last 30 minutes, what's the trending looking like? Last 1 hour, what's the trending looking like? So windowing operation. Pretty much whatever you can think of, even stateful operations, Spark streaming has a very rich set of high-level APIs. Second one is fault tolerant. Most streaming applications are fault tolerant, but it's just about the semantics. Do I support at least once semantics or exactly once? So when I say at least once, every event that comes in, is it going to be processed exactly once or at least once? This makes a big difference. And we'll spend extensive amount of time on this in the next few slides in fault tolerance. It's very difficult for the streaming application to support exactly one semantics, and Spark streaming supports it. In fact, Storm doesn't support exactly once. Maybe the Trident, which is like a next level abstraction on Storm, supports exactly once. But we'll see the details on that. The third point is actually the most important of everything. It has a very, very deep integration with the entire Spark ecosystem. The reason why this is important is, let's say whether you want to do Lambda architecture. One is real-time one, you want to do Storm, and in the batch processing, you're going to do maybe MapReduce. You're pretty much going to rewrite the code in both use cases, right? That's the majority. Or if you want to do, as part of the stream processing, you want to train your machine learning, train your models. It's not possible. You're going to rewrite it. Or you want to do a SQL lookup. Here, pretty much all these things are possible as part of the streaming application because it has a very tight integration with the Spark ecosystem per se. So, first we'll get a high-level view, what is Spark streaming is about. Then we'll go into details of each of the pieces. Spark streaming is nothing but you get streams of data. And the first thing what Spark streaming does is converts a stream of data into micro batches. There's a big difference between this and Storm, which we'll all discuss what is it, because Storm processes record by record. But here what it does is, it takes a stream of event, converts into micro batches, and then gives these micro batches to actual Spark, underlying Spark. So the underlying Spark does the execution. Here I want to give a little bit more detail. So Spark basically is not designed as a real-time system or as a streaming system. Spark was designed for a batch processing system. But it so happens that the batches are going to be like, the performance was very good, they started minimizing the batches. So here, as you keep minimizing the batches, you get a feeling it is like streaming. But it's not designed from the scratch as a streaming application. So that is how we achieve Spark streaming does the streaming process.
How it is different from IBM streams?
Infospace streams. We'll go there. Infospace streams and this one, Infospace streams you can see pretty much like how you do like Storm. Very high scale you want to handle it. You can do even by event processing, like any other Storm application is what Infospace streams is. The load on Spark streaming, suppose you might have use cases where you want to process record by record at a very high throughput rate. Then Spark is not the correct use case. You want to do Storm or Infospace streams. If you want a very high load, Infospace streams can handle very high load way better than Storm also. So now, this is about you receive the data, you do into micro batches, and then give it to Spark. But the next thing is, how do you run some of the operations as part of the streaming? So if you have worked in Spark, the basic thing is RDD is where the abstraction which helps you to do different transformations in Spark. So the architecture is very clean. Underlying core uses RDD to do all the operations. Now they wanted one other abstraction. The reason because RDD is one block of data. When it comes to streaming, you get multiple RDDs. So when I say micro batches, each batch is actually an RDD. So let's say we have micro batches, every second we cut a batch. Each batch is actually an RDD. So you need to perform operations on a group of RDDs. That is the basic. So they introduced a concept called D-stream, which is discretized stream. The discretized stream is nothing but a capability to run operations at a slightly higher level for a group of RDDs. That's all it is. And actually streaming, that's all it's all about. Because everything else, it imitates that underlying it goes runs on individual RDDs. That's all it is. So that's why the computation starts with D-stream. It internally generates RDD transformations. And once it generates RDD's transformation, thereafter it's everything about how Spark handles. The regular task scheduler comes into play, task scheduler comes into play. Everything is about Spark. Because we are not going to discuss this box because I think we have extensively discussed in the last 3 meetups about how that one is happening.
So what should be the size of this RDDs what you are cutting?
Which one?
Size of
the RDDs. Okay, it's a configurable one. It's called batch interval.
No, but what should be the ideal thing? Like it should be very small, very big.
That is up to your cluster configuration. It's not very straightforward. So let's say you want to say, I have a 100 node cluster and you want to use the entire 100 node for your streaming application. Then each node, let's say, is 3 core. You pretty much wanted 300 partitions. Now, we'll discuss a little more detail, but batch interval is after every batch, when do you want to run the computation? That is batch interval. But there is another thing called block interval. The partitions are batch interval divided by block interval. I'll get into the details. We'll come there. And in fact, we'll spend a lot of time on the next meetup where we do the performance tuning on this one. And we'll spend a lot of time tweaking this and seeing how it's done. The streaming application, there are only 2 big things, right? One is how do I receive data? The second one is how do I process data? That's pretty much any streaming application is going to do. So in the case of receiving data, everybody who has worked in Spark will pretty much know because for some level streaming, you need to know Spark at some level. Because otherwise it's very difficult for me to go explain what does Spark do. So I'm going to assume that you some level would have had an understanding about Spark, at least in theory. Because Spark master, which is the driver, which is where the code runs in. So the first thing what the driver does is, it starts a long running task called receiver in one of the executors. That's what it does. The goal of a receiver is, it can plug into most known queuing systems. Predominantly Spark uses Kafka as the major queue one. So let's say this receiver is plugged into an input source. which is Kafka. Now it starts getting streams of data from that. First thing this receiver does is, it creates blocks, data blocks, and stores it into local memory. The next thing what it does is, because if it is stored in one place, fault tolerant will be an issue because this is an in-memory data block. So what it does is, it does a replication of that to one other worker nodes and keeps it as a backup for the fault tolerant purpose. That's pretty much what it does. It keeps receiving data, it keeps storing it, divides into blocks of data, stores it in the memory, and then copies it to another node. Now, next thing is you need to process it. So when do I process it? Because it's not going to process in real time like Storm does, and as I get an event, it doesn't do it. So there is an interval call. Every batch interval, driver launches task to process the block. So there is a configuration variable called batch interval. If you want very high throughput, you can go a little lower, even 100 milliseconds fine. But you don't want to go too much lower also because the scheduling might take more time than the actual processing. Then the queue will get piled up. So every batch interval, the driver launches some task. And these tasks are pretty much same as how do you do any Spark processing. It will go, run the job, and spit out the output, do whatever transformation it has to do. So this is the basic about receiving and processing.
So the replication also happens in memory?
In memory. Okay. So that's why if both goes down or anything, fault tolerant is there. Fault tolerance will spend a lot of time.
So once that, like, you know, the interval finishes, when the processing completes, so the replication node also will get overridden by the new data. Is that what, or is it still?
No, it keeps adding.
You'll be still pile up even after the processing completes?
Once the processing is complete, you don't need it because it's in-memory processing. After that, you don't need it. So what's different from other streaming applications? So we'll see traditional stream processing systems, what do we do? Most stream processing systems do something like continuous operator model. What is that is, there are some operators which are running continuously where it processes each event, does some processing and spits an output. This is, you can assume in Storm. How many of you worked in Storm? Okay, so this is how your Bolt works, right? In the Bolt you keep picking data, do some processing, spit out output, this constantly you are doing it. There is. But here there is a different thing is, Storm processes record by record. In the case of Spark streaming, we said it's micro batches, it's not record by record processing. That's the first difference. Load balancing. So let's say in the case of Storm, if you have two bolts and you have explicitly set it up like the first bolt will process events 1 to 10, and the second one will process 11 to 20 like that. But unfortunately, if your 1 to 10 load is going to increase 3x times, there is no way for you to, and the other guy load is very less, assume. There is no way for you to share it. It is going to constantly choke that one guy because the bolt is explicitly designed to handle 1 to 10. There is no way for you to load balance. This is a standard problem in any continuous operator model. But in the Spark streaming, it's not like that. Because the way in which it does, it just picks up the data, splits into a bunch of partitions, and allow anybody can process. There is no restriction on who can process the data. The only difference here is you need to achieve some level of data locality. That is the most important thing. So the thing is about where the data resides is the most important thing. And anyway, if you're doing HDFS, you have some level of replication, 3-factor if you haven't, you have enough room to partition and run it. So the idea here is in the case of load balancing, all the nodes are evenly utilized at some level based on how you partition the data. In the case of continuous operator model, you cannot do it when the spike happens.
Can you tell a little more clear, because if in other streaming application, if there is a need for the board or whatever is to process a particular thing, are you saying there is a business need for that? What is the scenario for only 1 to 10 that will process?
So that is how streaming applications are designed, because you want to maintain the state of them. Let's say you want to do a count of the words. So only way I want to know, because I'm maintaining on the state on myself, only if I redirect to that place, I can keep a count of it. Let's say all words starting with AA, I need to keep a count. So I have to segregate that AA has to go to one bolt because that guy only keeps a counter of it. But here you can do it differently.
So you're saying you go to that kind of, what you're looking for is actually going to that type of a bolt. Right? It's a bolt specifically, but it could be running in different nodes actually, right?
No, you are going to run different nodes most of the time, but not on the same set. Will not run in different. If you are doing, so it depends on what type of analysis you do.
Yeah.
If you are doing analysis where most of the time, let's say I'm looking at trending on a particular topic, The only thing what you want to do is this particular topic, I need to get all the stream into one node so I understand the state of it. But if I'm partitioning on multiple, then I have to maintain a stateful guy outside of the stream where I have to go do an update and come back. Everybody goes to it. That will decrease the throughput.
What I'm saying, I think if you're really looking at streaming at a huge scale, you just can't depend on one node, right? I mean, that's anyhow going to block you.
Correct. That is what we are trying to tell you here in the Storm use case.
I think, okay, what I'm saying is actually if you're really looking for some kind of an count, how many people has shade up for India, Pakistan, final match or whatever, that will be millions. And you might not be able to do it in one bolt actually. Obviously you need some update.
You will do chunks of it.
Yeah.
But there is no guarantee that each of these chunks are evenly spread. That is the only thing. So you can't process in one node. We're not telling in Storm it has to be processed in one node. It will be processed across nodes, but you will set up some chunks of it, some range of it in one node.
Yeah.
If that range is going to spike 5x more than any other node, you cannot balance that one. That is the...
Okay.
The next one is node failure. So in the case of continuous operator model, let's say one of the node fails for some reason. Let's say and you are processing for 10 hours continuous streams. At the end of the 10 hours, it's failed. And you want to do something at the end of the 10 hours to do some consolidated reporting, trending, anything. But what really happens in this case is, when you start the back that node on the continuous operator model, you have to replay the stream from the start till the 10 hours end. Because that particular node has to catch up fully to that one. That is the only way you can do in the continuous operator model. But in the case of Spark streaming, it's slightly different. Let's say one particular node failed in. So the data set is with any place you can run the data set as long as the data is available locally in that node. Let's say for that data set, we have a replication factor of 2. The 2 different nodes also has data set. It's perfectly okay for you to spawn the process in 2 different nodes to catch up on it. The goal here is even if a node fails, rest of the nodes can take up the responsibility in the process as long as the data is available on that node. There is no restriction that you have to requeue the entire processing on the same node.
That replication factor also configurable?
Yes, that is a HTTP. Yes, it's configurable.
No. So this is in-memory replication you are talking about, right?
No. This is not in-memory replication. This is from some place you are loading the data and doing the process. HTTP replication is configurable.
That will be taken care by YARN or someone, right?
Which one?
That thing will be taken care by YARN, right?
No. Oh, replication factor you're telling. Yeah, replication factor you can set it up, whether through YARN or explicitly, it's up to you to set it up. But the processing changing the direction, the driver will take care of this one. Correct.
No, but earlier you said there is another replication in memory, some few slides like
As soon as you get a stream.
So that is different. That is for fault tolerant use case where a particular receiver goes down or something, then the driver knows to go back to another one.
But it's only about the collection of the data, not about the processing.
No, in the processing. In the same use case, for example, let's say I have 2 executors. The first executor in-memory data blocks are there, and if the data blocks goes down, you can easily, driver knows that I have to go back to another one. That is in-memory. Am I not clear?
So basically there are 2 replications now we are talking about here, right? So one is the in-memory and another one is the STSM.
Correct. So if you are doing your processing purely based on in-memory one, the in-memory replication, what Spark has in, that is what will use. But sometimes you want to go do a lookup on something and come back. That is when a persistent storage lookup only is done through as part of HDFS processing.
Okay. What are you talking here in this grade is whenever there is a particular task fails, then the fault address of a file signal comes into picture.
No. Sorry. I'm sorry. In this one, let's say this is the same use case as your regular replication, not HDFS. It's my mistake here. So this use case is, assume this is like your executor. This is another executor, this is another executor. This executor's in-memory is actually copied here, and another set of data. It doesn't mean that every time when you get the data, it is copied to only one. Assume 10 set of inputs got in here, 5 are copied here, 5 are copied here. Then the driver knows to start the jobs in other place. Sorry, I didn't look at the picture. This is not HDFS replication. This is pure in-memory receiver replication.
But then the backup is always in sync, or
Which one?
the backup will be always in sync?
There is no backup till now because it's all in memory.
Yeah, the in-memory thing also it will be always in sync.
Oh, that will be always in sync because I will explain how that in-memory sync will happen a little later. because that will be always synced. Then only it acknowledges, the receiver will acknowledge to the sender only when it writes both the in-memory operation.
What if the receiver fails?
Correct. When the receiver fails, driver has a capability to start the receiver. We'll explain in the fault tolerant use case. So this is very simple stream processing code. Just to want to get a hang of
the receiver in this case?
which one?
Who manages the receiver?
Driver manages the receiver. Correct. So the driver holds a full control of the receiver. It's another task running from the driver, like any other Spark task. So the key of anything, it's like a regular Spark program, but the only thing we want to give it is, there's a slight difference between a Spark context and a streaming context. That is the difference you want to note it down here. So when you do a stream processing application, you want to create a streaming context. The key thing on a streaming context is the second parameter, which is the batch interval. That is how often you want to start, that is the second one. So when you want to hook up to any stream, for example in the case of Kafka, Spark gives you all these utilities where you can go hook up and get the data. So that is Kafka util will do that. In the Kafka util, there are two ways to do it. There's a traditional way of getting the streams, and then there's a Kafka direct API. We'll go into all these differences a little later. So once you get a stream of data, this lines is the only difference. Let's say in the case of Spark, you go and read a file. What you will get is you will get an RDD. But in the case of here, you will get a D stream, because the lines is a D stream. And the lines internally contains a sequence of RDDs. That's pretty much it. So any further operation that you are doing on lines will actually result in another D stream object. That's the only difference. So in the case of RDD, you would have realized whenever you are doing any transformation, everything is lazy operation. Nothing really happens. The only time where anything will happen is when you see an action in one. In the case of Spark streaming, the action is the start of this one. So when you hit a start is when the entire processing keeps happening. Till then, nothing happens. So there's a correlation. If you want to associate yourself, RDD action will be some level same as streaming context at start.
Is this also a continuous running?
This is continuous running. The one that you saw there, the first diagram where a receiver doesn't. So once the driver is loaded with this code and it starts a long running receiver, it constantly keeps on processing this application. Till you explicitly go stop the streaming context, it will keep on processing.
So, and the processing starts only at the start statement, right?
Correct.
So, until that, if I am working on an interactive mode, so I have come till word count trend. So, even that time the streams will be coming. No.
No. So when this program is all loaded in driver, nothing happens till it hits it.
Yeah.
Literally nothing happens. Only when the start hits in, you will see even driver triggering a receiver task. Till then nothing happens. Just like sitting over there.
So how to, like if I want to stop in between, right, like if it is running now, my stream is complete, how to control that, to stop it?
Correct. So you have ways to stop the streaming context. I think Sachin will walk you through all the details when you do the code session.
So internally these streams are
Okay, so the question is, how do I stop the stream while the stream is processing constantly? That's a question. We'll walk through in the code part, so you can see the exact code.
Internally, this D stream is converted to RDD.
Internally, it is RDDs, nothing but. It's a stream of RDDs, collection of RDDs.
Kind of one more level of option.
Exactly.
I have a question here. What is the connection with data frames in this scenario? If it directly maps to RDDs, then are data frames totally irrelevant?
Yes, in this case, data frame is totally irrelevant.
irrelevant. No, we can use data frames in this.
But internally, you can convert to a data frame.
Internally, you have to convert.
You have to convert. Like ideally, if you do a transformation directly, it does an RDD transformation. But if you want to explicitly do an data frame, it gives you option, like a regular one.
So each stream can be converted into data.
No, so in D stream there is a function for each RDD, and for each RDD you can say RDD to two data frame, and then you have a data frame, you can write a SQL on top of it, right? You can do it.
You got the difference, right? It will by default do RDD only. If you want to do it, you have to convert to data frame. So fault tolerant use case. So here we'll explain every detail about fault tolerant. So why care about fault tolerance? See, there are two types of business models which exist here. There are some business model where data loss is not acceptable. Let's say payment systems, finance systems and all. But there are some other systems where search engine, it is doing some processing, trending. If I miss a couple of data here and there, no big deal. But a streaming application should ensure that it is very highly fault tolerant system. That's what we're going to do. So different guarantees for data loss. This I think we touched base in the start. We'll go into a lot more detail here. For example, there are business applications, let's say you're doing fraudulent transactions. You're checking for an e-commerce company. Those type of use cases, you need some guarantee that exactly once processing is happening in, you need to have the guarantee because you can't reevaluate the same data multiple times. But in the case of trending use case, like at least once guarantee is perfectly fine. If I miss here and there, not big is going to affect in my business model. So what all can fail? If you see the architecture of it, there are only two pieces in the Spark streaming application. There is one a driver, the other one is an executor. So if at all it's possible, any one of them can fail. That's always the total components itself available here. So this is the use case. Let's say a particular executor fails. This particular executor runs the driver and the data blocks it has. When a particular executor fails, driver detects the failure and driver automatically starts the receiver in another executor and starts all the tasks which has been processing in the other executor. Automatically driver will take care of you. In fact, you don't have to do anything on this configuration. This is what will happen when a particular receiver fails. Now, what happens when the driver fails? Because this is much more sensitive. If the driver fails, it actually all the executors fail, all the receivers fail, and all the in-memory data blocks, everything is washed away because driver is your master. Pretty much your whole cluster is gone. That is the use case when the driver fails. So whenever driver fails, you have to do all the processing to ensure. How do you ensure this is fault tolerant? So the first thing what you do is, how do the driver know that I have to start all these things? Everything that the driver knows is about the streaming context or the D-stream, DAG. Once it has the D-stream DAG, it knows how to do rest of the processing. So what you have to do it is, you need to regularly checkpoint the D-stream DAG into the some fault tolerant storage, which is HDFS compatible file system is what Spark Streaming today recommends you to do it. And once you do that, then there is a way for you to recover back, which we'll show you in the next one. So let's say a driver failed. The driver, when it restarts, we'll say go into a little more detail also, but what it does is when they started, it will try to read from the fault tolerant storage, it recreates a DAG. Once it recreates a DAG, it knows that it has to start again the receiver, again all the executors it will start. But there is a problem, because let's say at particular time T0, driver crashed. But at that point of T0, there are a lot of in-memory data blocks which would have existed in all these executors. So even though you come back and checkpoint and start the DAG, all the data would have been lost. You really can't do anything. That we will see it in the next use case, how we are going to handle it. But just to show, when the driver fails and you want to restart, what are the different things you need to do it? The first thing is, configure automatic driver restart. But if you're doing like a yarn, it will automatically take care of it. If it is in the standalone mode, if you run it as a cluster and you set the supervisor option, it will take care of automatically restarting. Second one is, set the checkpoint in the HDFS compatible file system. Because now the Spark only supports HDFS compatible file system. So you need to mention somewhere where these checkpoints, DAG informations are going to be stored. The third thing is the most important thing. So if you go to the original code, you want to go to the original code. In this code, there are two things are important. One is creating the streaming context still here is one part of it. The second part is actually starting the streaming context itself. These are the two things in there. So you need to realign your code in such a way where you are able to create a function and do all the setup upfront. There should be a curly braces here. Assume this is one function. All the setup is done on one function. Then, while you're actually creating the context to start, you give this function get or create, where you will mention the checkpoint of the HDFS directory and the function name. So what this line will do is, this line is very important. What it will do is when get or create, it will first try to see in the HDFS directory, do I have some checkpointing information, streaming context, do I have it? If it hasn't, it will read from there and create the context and start it. But if the HDFS directory is empty, that means there is no checkpointing happened in, it will go call this function and create the tag from the start. That is pretty much what it will do.
Okay, this is what helps when you restarting the driver.
Correct.
So, one question, can I? So, why do we use some kind of a clustering on a driver side? Why, why can't you use a cluster so that, they talk to themselves?
When you say cluster, is the driver itself multiple drivers?
Yeah, so what is it that it really depend on driver when they're processing? Is it that continuously they talk to it, or if they're doing the processing?
Okay, I'll explain. A little bit, this is about Spark basic. So, Spark works with a single master setup. So, that is basic architecture itself. The executor cannot do anything without the master. The entire control is with the master. The executor, what it does is only does the actual execution. So there is a concept which you guys would have seen before we ran in a couple of meetups, where there is a DAG scheduler, where a DAG is taken, cuts into multiple stages. Then there is a task scheduler, it takes a stage, split into multiple tasks. All these are done at the driver. What finally it will do is, it will take one task, which is one partition data, and what it needs to run as part of that particular partition data. Till then the driver will do every work, and will give that to the executor. You go execute and give it back to you. So executor is like pretty much very dumb. Doesn't do anything.
So then making the driver as clustered makes a lot of sense, because if you really do a lot of this restarts, if you run into the scenario, restoring is always like a pain, right? Why can't we?
Okay, so this is the basic of the architecture. I'll explain why. It is quite difficult to accomplish. The reason because the whole control of the DAG, how it's processing, if I am splitting, there's no way for you to split, right? Because the DAG is a single DAG which you're executing. So we will take this offline where I have to explain a little bit basics about how Spark is designed. Okay, so now we know that when the driver restarted, we still had a huge data loss because all the data, in-memory data blocks which live on the executor side are actually wiped out. Now, how do you ensure there is no data loss? So what we'll do is, there is another persistent storage which we are going to create on the executor side. So as the receiver keeps receiving data, the receiver will write the data synchronously to a fault tolerant storage, which is also another HDFS compatible system. But this is a sync call. Only when this one is successful, it handshakes with the queue and tells that I am done, so I am acknowledging, send me the next one. So this is the one way, and you'll see how this one is useful in the next part.
Sorry. Because of this block getting saved off to HDFS, is there an overhead?
Yes, yes, you have an overhead. See, because when you do stream processing, there's a big difference between you doing in-memory stream processing and you are writing every time as a receiver is getting to a disk write. Because you have to serialize, there's a network bandwidth, there's a disk write, everything is involved, right? So there is an overhead, but it depends on what type of streaming application you want to run. If you want a very high fault tolerant, no data loss system, you have to go through this one. There's no way for it.
So who manages all this information? Like, driver manages?
Which one?
So the information about the block saved in HDFS.
Yes.
So who manages that?
So the executor sends these information as meta information back to the driver, but the driver keeps it locally on this, and then it will send it back when it restarts. And I'll walk you through that detail also a little later. But every meta information driver manages, but who sends it is when the receiver writes it locally to the HDFS file system. As part of that, receiver will send the meta information to the driver, and driver keeps persisting that meta block information in another fault tolerant storage, which it will use it when it resends a task back to the executor, which we'll go into the detail also.
Just one more question. When we run this with Hadoop, right? So here active driver will be running along with the application master?
Correct. So you have two options, right? Either in a YARN mode, you can run as a YARN client mode or a cluster mode. Driver can be run in both ways. So if you don't want the driver to be run as part of your YARN cluster, you can sit outside in a YARN client mode, you can run it.
If it is running in cluster, so
the driver will be inside the Spark cluster itself. Correct. But even in the client mode, there will be an application master created, but it's a lightweight way, not the full driver code existing.
yeah, but driver will be driver master.
Correct.
In the client.
Correct.
If we are using Kafka as the source of the data, then do we need this write ahead lock? Because we can replay it from the Kafka, right?
So that is quite a different one. That's a good point. So actually, I'll explain a little bit. That's a very good point. See, there are two systems which exist here. One is Spark as a system, then Kafka as a system is separate. But you know Kafka you can replay. But the key problem is Spark should be able to recover automatically wherever possible. But because it's a constant streaming application, right? You don't want every time to go replay from Kafka as long as you're completely living within Spark. We'll go into that also. There is a specific topic where we'll discuss these two. These two are two different systems. If you have a local copy by yourself and you can replay automatically, it has much more control on the Spark instead of, so let me spend maybe a little bit of that. Assume if you are constantly processing. Now, at one time, this particular node or the driver went down. Okay? When the driver comes up, how do you detect where in Kafka you failed, which offset you failed in?
Yeah.
Automatically, there is no way for you to detect. Unless you write that offset to some other place, maybe a zookeeper or somewhere. And then you have to go read that one, and then you have to send a trigger back, right? Instead, you're better off within the Spark architecture, if it fits in, where I come back, the executor already sent where it wrote to me, so I directly send the request, go read from there and start executing. This is much more cleaner setup, right?
And also that may require a lot of handshake between Kafka and
Correct.
It is not mandatory to use Kafka. You can use Flume, you can use socket stream, you can use file stream. In that case, how will you?
Correct. In the case where some of the queuing systems cannot even replay the queue, because Kafka has the capability, but some of the queues may not be even able to replay. So then this is the use case. Okay. To enable val, you need to do set of configuration. Same thing. You need to enable checkpointing. You need to enable val itself, that is that variable. Receiver should acknowledge the input source after the data returned to the val. That's what we're telling, right? As and when it keeps receiving, it will synchronously write to the val and then it will handshake to the sender. It can be Kafka or anybody, so that it knows that I have written synchronously, so the data is always there in the fault tolerant storage. Disable in-memory replication. So this is the important one. So till now, whenever we get the replication, whenever we get it in the receiver, we replicate the data blocks to one other place. But this time we can disable, because since we have already written to a HDFS compatible file system, HDFS replication will take into play here. So that's why you disable, because it's unnecessary overhead that you are going to have.
But isn't it better that it tries to recover from memory first rather than actually going to HDFS?
So when the driver fails in, even if you have an in-memory replication there, it will go away. That's what we saw, right? So let's say you have two executors there. This is the use case where the driver goes down. When the driver goes down, everything is washed off. The executor, receiver, data blocks, everything. So there is no way for you to recover with that. So you need to have a fault tolerant storage.
Here, how we can make the receiver acknowledgeable? Do we need to do anything from our side?
Yes, you will do where you have to. With Kafka, it is already inbuilt. You will figure it out. But let's say you are writing completely for a new input stream one, then you need to take care how to handshake with the input.
So if we need to do coding from that one,
If the input is like completely different, which is not in any of the Spark input streams, yes, you need to write it yourself.
So here it's more of a recommendation to disable in-memory replication.
Correct. It's just a recommendation. But if you want to have it, you can still have it, but it's not really useful. That's one thing. Can't really hear.
Can you repeat the question also?
On the receiver, you said there is a replication of data created on another receiver. So that is also washed out when the driver goes down.
Correct.
So that is stored in the driver itself.
When the driver goes are gone, all the executors are gone. When the executors are gone, it internally means the receiver running on the executor is gone. The data blocks which are living in memory on the executor is also gone. Like literally the whole cluster is gone when the driver goes down. Driver is really like a master.
But Paranth, the point is that you don't know whether the driver is going down or whether the executor is going down.
Correct.
So you still probably need to enable the in-memory replication.
Correct. Each of this use case is very different. But when you enable this guy, let's say if you have from the receiver side, if you are writing it to a fault tolerant storage, it automatically ensures you have fault tolerant. But having said that, what Pawan is telling is also a good point. So let's say I am writing a fault tolerant storage system. I don't know at what time my receiver goes down or not. Let's say my receiver went down. You still have the capability to read from HDFS and you can replay. That is also possible. But if you have an in-memory storage somewhere else, the driver automatically can run the show also. It's up to you to say how much I want to keep the fault tolerant.
So the fault tolerance storage is used only when the driver goes down. It's not
No, for this particular section, we are telling about driver going down. But if in the other case where the executor goes down, at that point you had an in-memory copy of it, so you're perfectly okay for that particular use case.
To access the fault tolerance storage at all if the executor goes down.
Your executor goes down, you don't have to anything write explicitly. Spark automatically will take care of it. This is the full picture, which is I think you are asking it. So this will completely tell what all will do on a normal processing and what all will happen when the driver comes back. So from the input stream, there is a receiver will keep receiving data. After that, it will keep writing the memory data blocks to the local memory first. As part of that, it will write to a fault tolerant storage, which is in a HDFS compatible system. Now once it has written that, the receiver will send the block metadata to the streaming context to the driver. As part of the block metadata, what all it will send is two informations it will send. It will send the reference ID for the memory written in the in-memory data blocks. It will also send the offset informations of the data which is in the fault tolerant storage. These are the two things it will send to the driver. The driver will have to save this metadata somewhere. So the driver will process this metadata in another fault tolerant storage and keep the metadata. As part of that, driver will also checkpoint the tag that it is running in another fault tolerant storage. These are the things on a normal processing it will do. Once it does these two, it will kick off the jobs and it will give it to the Spark context. Once it does this, it is a regular processing. After that, how Spark does is the regular processing.
This is almost similar to what happens in STSM, like the data node creates the block and then it sends back the metadata to name node.
Correct.
And name node maintains its
pretty much the same. So now when the driver restarts, the first thing what the driver will do is, it has to know what is the DAG that is executing. So it reads from the fault tolerant storage, so now it has a D-stream context. The next thing is, it needs to trigger the task on the executor. But when it has to trigger the task to the executor, it needs to tell a task is nothing but data plus the actual computation. Because it loads the D stream, it knows what transformation to execute. But it has to tell the executor where is the data available. To tell the executor where the data is available, the only way driver knows is whatever meta it wrote on the fault tolerant storage, it reads from there. So with these two informations, driver exactly knows what is the computation I had to tell and what is the data I had to give it to the task manager. Then it restarts the Spark. Go to the Spark context and starts a regular job. As part of that, what the receiver will do is, using that meta, the receiver will either know that I had to run from in-memory, or it knows that I had to go to my fault tolerant storage, using the offset which the driver gave, it will go read the data and start the process. This is pretty much a standard flow. When the driver fails, what will happen to the computer?
What is the recent data, sir? The stream?
Which one?
Like recent data.
So whenever you're finished processing with this, it acknowledges the data, right? At some time, unacknowledged data which is there, the other side queue will know that I had to resend. So let's say,
so other side in the sense it will be
Kafka. Okay. So let's say we keep receiving it and we wrote to the fault tolerant storage. After that point, driver crashed, but Kafka kept on receiving.
This holds good if you are using Kafka. Let's say I am using some other streaming data, like stock tick level data which I keep getting. So in that case, what happens?
You lost the data. For that point of time, you lost the data because your queue cannot reproduce that, and your system is down.
So let's say for any system on the other side, if you are able to do handshaking only, you can ensure no data loss. If you are not able to handshake with the other system, there will be always a data loss. But it doesn't matter Kafka, any system where you can handshake.
But you are pulling the data, right?
Kafka is not sending, you are pulling from Kafka.
Correct. You're pulling. So that's why you can handshake. When I write it and finish it, I tell them I am successfully done. We'll tell you how it is done. We'll write to the offset, which we'll discuss in the next one. Give me 1 minute. I have one more section where we'll exactly say what we're doing.
So once you finish processing, right, how do you clear up the data from HDFS?
I can't hear.
Once you finish up the data from, so once you finish the processing of the data, right, now you have metadata from multiple data replicated in HDFS. How do you clean that up? Does Spark take care of that?
Oh, this fault tolerance storage of clearing up that one, huh? That one Spark automatically will not take care of.
You have to do something because
You have to do.
you are streaming from web blog, right? It's a website.
Correct.
You can easily consume your space, right? Free application station.
I am not sure. I had to come back and check it out. Do you know whether this fault tolerance storage? The question is this fault tolerance storage cleanup happens automatically as part of the job processing? That means when the job is done, there is no done here. It's constantly running. I had to come back. I'm not sure.
There might be a roller and flusher inside it.
Which one?
Log roller and log flusher, which might be running compression techniques and food processes.
So then I'm not sure. So I'll tell you why I'm little doubtful on this one is, see, if you're running a regular Spark job, which comes up, executes, goes down, I can flush it because I can build it. But this is not a job which will ever come down. You're constantly running forever. So that is why, I don't know, I had to come back. If anybody knows, then we can give it a try. But we'll come back on this one. There are some things which are written over there, which is not coming in there.
Can you see now? No, it's not there. Can you check that right color?
Change the resolution.
Hello. So, yeah, rolling briefings. Okay. So now, how do you ensure you have fault tolerance semantics, right? There are three pieces in this whole processing. There is one which is receiving data, one that is transforming data, and one that is outputting the data. So this is pretty much B-stream or RDD processing. This is always exactly once because that is how underlying Spark does is RDD processing, which always guarantees you exactly once processing. There is no issue on the transformation part of it. The outputting part of it, as long as the outputting system which you are spitting out, or let's say you call a service and that service has to do something. If that service is either idempotent, it is perfectly fine because let's say even if you received more data, that means at least once guarantee you receive the duplicating data, but I'm sending it there and that guy is idempotent, he'll always ensure it is exactly once processing. If idempotency is not possible, you need to build in atomicity using some level of transaction-based one for the output. But the receiving is a real problem. So when you receive the data, so let's say you receive the data and you wrote it to val, that is the fault tolerance storage receiver. This is where it comes in what you are asking in. When it comes in, then there is two offsets maintained. One is Spark thinks it that I have storage, but Kafka knows the only way is what offset is available in the zookeeper is what Kafka thinks that this is what is the last one available. So every time when, let's say you wrote it to val, but before you write it to zookeeper, let's say the particular executor crashed. At this time what will happen is Spark thinks I have this data, but Kafka thinks that I haven't sent this data because it's still in there. So when you go back and use the offset and go pull the data again, you're going to pull the data, the previous one. That's a duplicate data will always come in. So that is why you will have at least once guarantee. That means you might have a data duplication here. But when you have data duplication here, you're going to have that same data duplication across the places, some level. Okay. So the receiver part of it, receiver does two things, right? One is it receives the data and writes to a fault tolerant storage. So that is from a Spark perspective. The only perspective where till which offset Kafka has sent it, that state or the offset is stored in zookeeper. So now receiver got the data and it wrote to val, but before the Kafka zookeeper offset is updated, receiver crashed. At this time, Kafka's impression is, because offset is an old offset, I haven't sent this data, but Spark already has this data. So what will happen is, when you pull the data again, Kafka will resend the already sent data. That is it.
Excuse me. In a standalone mode, what is a fault tolerance storage?
What is the fault tolerance? You can use HDFS also.
Okay. Other than HDFS?
S3, whichever one you want. What is your move? Anything HDFS compatible file system will work.
If it is in the local, then
you can run local also, but those are the problems which you will have. If you do local, checkpointing you cannot do. Like when you're doing checkpointing, Spark enforces that you use a HDFS compatible file system. Because the reason it doesn't allow you is it needs to have replication built into the file system. That is the reason it doesn't.
Okay. It is trying to leverage the fault tolerance provided by
of the HDFS. Correct.
So using any non-distributed file system doesn't make sense.
Exactly. That's why it enforces the one. Okay. So now we'll see about, there are two parts in this one. So Spark generally recommends going with Kafka. So they have done a lot of optimization specific for the case of Kafka. So we'll see what all they have done. So there are two sets of Kafka API. There's a traditional one before Kafka Direct, and there's a next generation is Kafka Direct. So till now, whatever we went through is all before the Kafka Direct, before the latest one. I think Kafka Direct came in 1.3, right? 1.3 maybe Spark. So that is when you have all the receivers, Val, everything exists only before the Kafka Direct. In the Kafka Direct, there is actually no receiver concept. There is no need for Val. Nothing is there. We'll see the difference. So ideally what will happen is here, every time we pull the data from the receiver before the Kafka Direct, this is a regular one. We write to Val, we write the offset to Zookeeper, and then the next time when Kafka has to send it, uses the offset, and then we pull the data from there and start processing. This is a regular, I think we already saw this one. In the Kafka Direct is quite different. Kafka Direct, I think we have a code for the Kafka Direct. So Kafka Direct is, you can assume that the whole Kafka queue is like a file system. You guys would have read file system in any C-based or anything, right? Where I have an offset and I keep moving the offset. I do L-seek, I keep moving it wherever I want to move. But ideally what you're telling is, I have one offset and I keep on moving the information, right? So the reason why Kafka Direct came itself is because there was a data loss in the previous use case, which we already saw. Or not data loss, it's the at least once processing problem was there. That is the reason the next generation came up, which is a Kafka Direct, because Spark wants to process exactly one semantics, which is very sensitive for many business use cases. That's the reason why it evolved also. So now, and you already got it, right? There are two different offsets living in two different systems. Spark has one thing, Kafka has a different place, the state of it. When two different systems maintain two different state, it's very difficult to maintain atomicity between these two. Because two of them have different state, right? Between these two update of the states, system can go down. So you need to always have the state where it is there, control should be in only one place. Then only you can ensure exactly one semantics. So Kafka Direct is meant to be like a file system, keep one offset and keep on reading the file as and when we move. So in this case, there is no need for a receiver at all. What it will do is, every time when the batch starts it, it will exactly determine till what offset I should keep processing it. And uses that offset and goes grabs the data and does the processing. The only place where it maintains is, it maintains offset in one checkpoint information. So every time as it comes up, it determines how much I have to read from this offset, uses that offset, go grabs it and come back. So there's no control on the Kafka side, nothing. It's purely on a Spark-based checkpointing is the only offset it has, and it keeps on reading like a file stream. Now there's a lot of benefit on this approach. Previously, let's say you have Kafka has 10 partitions. What you need to do to parallelism is, you need to start creating input D streams, 10 input D streams you need to create, you need to do a union of them, and you need to do all these things. But here what will happen is, each RDD partition will be mapped to one Kafka partition directly. So that is how the Kafka Direct API is written. So automatically they know that if I have 10 Kafka partitions, 10 RDD partitions will parallelly read from them. So the parallelism is the highest. That is one benefit. The second benefit is less storage need. If you see originally in the val use case, Kafka has some, let's say, terabyte of data. This terabyte of data is also persisted in some place, and then the val persists that same terabyte of data again in HDFS compatible file system. There are two times you are persisting this information. So in the Kafka Direct use case, the val doesn't come at all, so you have the data in only one place. From a hardware perspective, very less storage is the second one. And exactly one semantics is achieved because the state is stored in only on the Spark side. There is no two different state. That is a key thing. And you'll see a demo of this.
Actually, here there is no receiver, right? So how Spark framework will receive the data?
From the Kafka directly go. There is a new one which API we use. Simple API. Kafka simple API. We'll go use the offset, tell the offset, and directly put the data.
You are using simple consumer.
This is a simple one.
So is there any disadvantage for this? Any disadvantage or any somewhat?
Any disadvantage of this one?
Any use case?
At this point, I don't know. Do you have any? So yes. So this use case, right? Because Spark is pushing heavily into Kafka, or Spark thinks like Kafka is the best suit. There's a lot of things happening specific for Kafka than for any other queuing one. But it's not tightly coupled, I would say, because the reason is it's a regular simple API it's using. Anybody else, if they're using Kafka, you will end up using maybe simple API.
So how about fault tolerance now here?
Which one? Because the checkpointing is there, right? So the offset is checkpointed, and then only it handshakes it. So the offset is checkpointed, then when it comes up, it uses the checkpointed offset to go pull from the next one.
No, but let's say it has pulled some data and then it failed in between.
Then there is no problem because anyway it didn't process.
But it didn't finish processing, so now how about that data?
It pulled the data, and it didn't finish processing, it crashed. So ideally there is no problem because the old data is what the offset is there.
But it thinks that it has read already that data, so how to read it again?
Oh, no. So once it finished the processing, only the checkpointing will happen. So time t0, it read the data, process the data, then it writes the offset down. So now, like time t1, it comes in, let's say it pulled in and it crashed before processing. So what we'll do is the offset is t0, it will go read the offset and go read it.
It's exactly like file-reading function.
Exactly, that is what it will do. There is no other way, right? It's very simple.
Whatever stream you are at, then only you are moving the offset.
Exactly. So any place where you are maintaining offset for consistency is exactly what you do. You'll process and then you'll write it over.
And one more question now.
We are using this direct API. Suppose in Kafka topic there are 10 partitions. So when doing the streaming, right?
Yes.
Single RDD 10 partitions. Yes.
Okay.
Yes. So the basics, little bit, let me explain the batch interval and the block interval so that we get a hang of it also. So whenever you start reading it, every batch interval, it creates one RDD. That means, let's say we set up a batch interval as 10 seconds. So every 10 seconds, there is one RDD created, and the next 10 seconds, another RDD is created. Now the problem is, at the end of the 10 seconds only, Spark kicks off the processing. After the batch interval only, it said go kick off the job and run the job for the data that I received. Now, you need to have a way to fine tune this RDD, how many partitions I should have. Because the number of partitions will tell you how much parallelism you can achieve. The best way to do that is there is another variable called block interval. So the number of partitions, the formula to apply is batch interval by block interval. Let's say 10 seconds is your batch interval and you have capability to run 5 parallelism once, then you set the block interval as 2. If you want to increase the batches, partitions like very big, keep on reducing your block interval. So you can like 100,000, then you can go in milliseconds also. But 50 milliseconds is the best use case I recommended because more than that, you will see in the Spark UI, if the processing time is going to take more than the actual scheduling time, you will see it keeps on piling up, the RDDs keeps on piling up. And once that happens, your system is going to fall back because the queue is, you're going to constantly fall back and one time it's going to become unstable. So you need to have the combinations in such a way that your batch interval, you're able to constantly process the batch data that you're getting. These two are the, just to get a hang of it so that you got these two. Yes?
So, you were saying about checkpoints, right? So at checkpoints, if suppose I have read some data, switch on. Suppose I have read some data, and then it has processed that data and written the results also. So before giving handshake to the driver, to the sender, again if it fails, the reprocessing will start from the previous checkpoint. But then there will be communication, right?
The checkpoint is actually done before you handshake. You read process checkpoint.
Yeah, so once it has read the next partition, it will again and process it will again send a checkpoint, right?
So when it crashed and it came back, That use case is what you're telling me.
Yeah.
When it comes back, it always knows from last checkpoint where I am in, successfully written. From the next one, it will start reading.
I'm asking like suppose I'm the receiver. I have read after a checkpoint I have read one mode partition. I have processed it, and now I have stored the results.
In the checkpointed one.
Yeah, I was about to send a handshake.
There is no handshake in the direct API. So let me explain to you. That is the only difference. Direct API has no handshaking. You assume there is a file there. Okay?
But on top of it, one small question. There is no handshake, but what he's saying also makes sense. Like you have done the processing, but after processing you update the checkpoint with the offset of the Kafka, right? But before doing that, if you crash down, then you again start with the last offset and you will redo the processing again, the same thing. So, are you getting my point? So,
Okay.
the same thing will be reprocessed again.
I think he's saying when a task or crashes, what will happen if he has processed some data and checkpoint that part and some data is not processed, he will start from the first initial offset or he will start from the checkpointing offset.
Yes.
If a task crashes in a direct API, he will redo all the work. Kafka is a persistent storage, he knows from where offset to where offset he has to read it. We don't care about it. He says, okay, I have to read 100 to 200, let's say assume Kafka is a file. You have to read 100 to 200 lines. You crashed after doing 150, you leave the processing. Start from 100 to 100 and do it.
What is his point? The question is, there's a very small, there's no atomicity involved here. So if it's like a transaction block, you receive 10 records or 10 bytes from Kafka. And you start the job. Okay, so you start the processing and then you write it to, you checkpoint the information. Let's say you checkpoint it. Between the processing and the checkpointing, if I fail, what will happen is this question.
Whenever an executor in direct fails, he knows what is the offsets. Only offsets are checkpointed. He goes to the checkpoint, he knows this offset I was processing, he restarts that.
There is a duplication will come now.
Only offsets are checkpointed, not the data.
So basically it's exactly once processing. No, sorry, at least one processing.
No, there won't be any duplication. Whatever processing he has done is removed from the system.
But after processing, you might be updating some database or you might be updating some.
If you're writing up the result already
before
and then doing the
checkpointing the offset of the Kafka.
So the only confusion I have is do I checkpoint and then process or not is what I am.
Yeah. So basically it will be at least once processing.
Okay. Let me take this question. After the break, I'll give you an answer. Let me think through it a little bit. So we'll take a break. I think we're pretty much done. Driver itself fails is very straightforward, right? All the six. It will start with the DAG one, whatever we went through, right? It will start the history.
Sachin.
Is it visible at the back? So I hope everybody have tried word count from MapReduce. So we'll start from that same place. So what we usually do in word count, we'll see from this line. Let's assume somewhere we read files.
You sit that side, that code.
The code, yours not, the code is.
Sit that corner.
That side.
Because we cannot see.
But there also
Code is not visible?
Yeah. We cannot see behind you.
Okay. If it is there, we will not be able.
You have to put it in your lap.
So now, I can't see you guys, just say yes or no when you want to know. So when we do word count, we simply read a file and we process line by line. So let's say somewhere we read a file, in word count, we read a file, we got lines from it, lines object. Now on lines object, we are doing a flat map operation. And for like those who are new to Scala, I can take it flat map, 1 second for flat map. Flat map, what it does, it's like a map operation. So he will do a map and then transpose, you can assume it as a map plus transpose. So you have a line, you are splitting it on a space. So you got series of words. Now you do a transpose of it, you got words in each row, one word in each row. So that operation you can map with the flat map operation. So flat map will do the same task. Underscore is a way in Scala to tell that any random variable, you don't need to name a variable, you put underscore in place of variable, then you say whatever is coming, do this operation. So in the lines, we are doing a flat map where say line came inside one line. For that line, split it on space and do a flat map. That means you will get words, one word in each line out of this. So you got a words RDD. So words RDD consists of, let the line was, this is a demo example, then you will get this is demo example in each one of the lines. Now what I am doing, words is there, I am mapping words. So there is a word, only word, this is there. Now I have to append one in front of it. So I am creating a tuple out of it. For each word I am saying word comma 1. So it will make this comma 1 as one tuple. Second one will be is comma 1, then code comma 1, then example comma 1. Okay, this will become a RDD against. This is a pair RDD in which word comma 1 is there. Then there is a word count. Word count, what I am doing, pairs is my RDD. I am doing a reduce by key operation. And again underscore is here. So when you see this underscore, assume it is a x plus y. Okay. Now how this reduce by key will work? It's like fold plus summation operation. So you have this one is 1, code 1, example 1. Now I again replay the same line. So there will be this comma 1 again. Now wherever is a key same, you will do plus 4, 1 and 1. So this plus operation says whatever is your value part, key value, where is a key is matching, do value plus value 1 plus value 2. Now you got value 3. Now next time do value 3 plus value 4. Okay. So you are just folding all the values for the same key. So you have this one, this one, this one. So you will get this 2, then there will be this one, then again 1 got added, you will get this 3. So it's a fold or kind of operation. So now you know these 3 lines and word count is done. Loop for?
Like for one, or like for all the lines you want to do.
So for all the lines. So
loop, how you are doing that?
So,
I didn't see anything.
So there is a lines operation. This is a streaming part. So this code works for one line.
Okay.
Now when next line will come, same code will come. Okay. And lines is a RDD. It consists of, let's say, so D stream is a batch of RDDs. Each RDD has 100 lines. Assumption. Let's say or RDD configuration like that. I got 100 lines. Now lines.flatmap means for each line do this operation. Words.map is for each word do this operation. So for each is inbuilt in this. So you are, so assume RDD as array of anything, and you do for array dot for each. This is inbuilt in this. So these are collection APIs. Flat map, map. These are operations on collection. So if you say vector dot, then it means everything inside all the vectors it will operate. So difference between flat map and map is the transpose part. I told you that for flat map you can see as map plus transpose. So flat map what did? For each word he did added a 1 in front of it. So for each line he is adding something. But flat map will each line it will split plus he will make it more lines out. So it's not 1 to 1. Map is 1 to 1. One line goes in, one line comes out. Flat map is one line goes in and n lines comes out because of the transpose part.
So aggregation keeps on happening line by line.
Aggregation
of the keys.
Aggregation of the keys keeps on happening line by line. Yes. So let's say you have 10 keys, you have 10 keys and you have 100 lines. 10 keys are repeating. So for each key, you will keep on doing plus plus for value
instead of populating entire.
Instead of populating. So 3 lines your word count is done. You don't need anything other than these 3 lines in Scala. Now if you have written this code into a normal RDD fashion, in a batch processing, you will simply read a file, you will write a read file operation here. But if you go to streaming, you just say socket text stream and or text file text stream or Kafka stream, whatever is your source, just write the source on top and add a start operation below. So that means there is no change from the batch to streaming. Only change is source you have to tell, because source is changing in streaming. Your operation remains the same as it is, no change. And this word count.print is to print. You can append this also there and add spaces there. This is only for streaming part separately. Now I will show you one example for Kafka. How Kafka this example will change. Okay. So this is our same code which we had previous. There is no change in this code. How you are reading from Kafka? Kafka utils.create string, and whatever parameters it takes, you have to create those parameters. That is everywhere same. If you are connecting to a source, you have to provide the credentials to connect to that source, or description about how to connect to that source, and then in the last you have to say start. So moving from batch to streaming is pretty easy in Spark.
So last line, what is the await termination method?
Await termination is until we explicitly call him to terminate, he will keep on running. Let's say right now there is no stream we have. This code is there, I will simply run this code. So this code will keep on running until I say terminate. He is waiting for user action to terminate. Okay, so now there is no stream coming, nothing, just keep on running. He is waiting, something will come from that socket, something will come, just not nothing. Unless I terminate it, he keeps on running. So that's a function await termination. Wait for user action to terminate.
Does it have any default?
We have an integration already for any kind of REST API to easily apply.
REST API means?
You read it from a service.
You need from Kafka or something that then
like an
API. Yeah, you make a REST API call and then do it. I have not tried it.
Sachin, why it is showing the time 144 and we have got 2 seconds right here? This 144
milliseconds, no?
Yeah, what is
2000?
2 seconds.
Say 88, 90, 92, 2000 milliseconds is a 2 seconds. Not tried API calls, we will check that and we'll. Right now I have examples for socket stream, Twitter call, Kafka and direct Kafka. 4 examples. So we'll stop this. So now I can run few of them. Should I run them or should just go through the code?
Go through the code, if we can run.
Okay, we will cover all the concepts first, then we can run it. Otherwise, I have posted this code on the GitHub. Everyone can check it out from there, and almost the same code you can find it in Spark GitHub also. They are also posting the examples. So next concept in this is batch interval and block interval. So this. So in this I have made little modifications to the word count example. What I have done, I have specified here Spark streaming block interval. Previous one it is 2 seconds. Now I have told block interval is 100 seconds. So for there is two configurations, block interval and batch interval. Okay. So block interval you tell when to create an RDD. Block or batch? Batch you tell when to create an RDD. Block interval you tell when to create a partition. Okay. So this is milliseconds, 100 milliseconds. Right now we are giving 2 seconds here and 100 milliseconds here. That means 2000 divided by 120 partitions should create. I have to start some example, then only I will do this. So by running this. So what is happening here? Oh, I have to come back one line. So now what we did. So what we are doing here, this is our line what we are reading. So we call a repartition function on top of it. Normally it should print like 2000 divided by 120 as a partition. But we don't have 20 cores in our cluster to process. So we did a repartition for 5. So now if you run this code, you will get a repartition count as 5. So now if you can see, partition count is 5 here. So what is happening here, I have a repartition operation, repartition 5, and then for each RDD, this is very powerful operation in this, for each RDD you can use any RDD function within inside it. I am passing a function, do this function, and in this function I am simply calling rdd.partition.length. So I am asking RDD how many partitions you have and just printing that. But if you don't use this repartition part here, and you simply go ahead with whatever lines you are getting and then same call for same function on this lines operator, lines RDD. You run this again. Now there is no data, no partitions here. Now we will break, count is 2, count is 0, no data in next, no data. So based on number, I have to stuff so much data in it that it will go maximum up to this number 20. So if there is less data, you will say less than that. So now it reads 15, then it reads 11, then again back to 0. So whatever data he is getting, he is stuffing into the partitions based on the maximum it can go up to batch interval divided by block interval. Okay, I can move on to the next example. Next is stateful operations. How will you do stateful operations in Spark streaming? So you can read a stream, you can do word count, now you can do repartition based on your cluster. Next is how to do stateful operations. So in this there is a function update state by key. So use this function, you have to provide a function how to update your states. So let's say I am giving now, I don't want to do word count for each key, give me total count or something. So I can use this update state by key and keep on updating the function. So when you do word count, RDD, dstream is a collection of RDDs, let's name them RDD1, RDD2, RDD3. Now I have 3 RDDs. So when word count will run on RDD1, you will give only the count of the word within RDD1. You won't go to RDD2 count. Now I want to do whatever RDDs are processed till now, give me the count of total. RDD1 plus RDD2 plus RDD3. Then I will use pairs. On pairs I will use update state by key function and I pass a function. This function itself takes another function as a parameter, and this function I have defined here. What this function will do? So this function maintains states. So there is a one already state present. So the previous state is marked as a state. I have to explain option also. So option is a way in Scala to tell there is a you may get a value out of it or you may not get a value out of it. So there is a variable. So in Java we always say not equal to null, dot is empty. That you don't need to do if you are defining an option and everything here. So if you define the option, you simply say get or else. So if there is a value,
something similar, optional. So with Java 8.
Java 8.
Optionally.
When I mention Java, it's not 8, it's 7 because I never worked on it. So there is a get or else function in this option. So it says if there is a value, I will give you value. Otherwise, pass me something that I can return it to you. So say get or else, then put in strings 1. So if there is a value, you will get a value. Otherwise, you will get 1. So option is fine. So there is a state, previous state, and what value you are getting now. So he will say value dot fold left because you need to add for that RDD also and previous. So he will do previous same this RDD additions. Then he will add it to the previous count. So RDD1, the state will be 0. Then you will get some keys and some count. He will do a sum count there, word count, and he will store it to the previous state. Next, when RDD2 will come, for that key there will be some count here. He will update that count. So this will be stateful operation that RDD1, 2, 3. Finally, you will get total word counts, full stream from beginning to the current state.
So is it kind of a, when you say full, because it's kind of stream continuously runs, is there a window you're talking about?
No, there is no window. It's from beginning to the current state.
So
window will come later on. Window I have example I can show.
Okay, so it says always at that point of time what is the total count it's going to produce?
Yes. Let's say there is something kind. You are saying how many users came till this time from morning.
Yeah, it's kind of a
phase counter kind of thing. So there are two use cases. One is you want to see top popular keywords on Twitter or popular hashtag in last 30 seconds or total hashtags from morning. So this operation is total hashtags from the day start. Window operation is popular hashtags in last 30 seconds or last 60 seconds. That we will do in another example. And for streaming you have to do checkpointing. So I am right now doing simple checkpointing.
But this will keep on printing, right? Every
question?
In this one, when you are saying it is from the beginning, right? But so this counter will keep on getting printed once in a while.
Printed in a while.
Using pairs dot print. That will output okay, how much whatever number.
Yes, for let's say RDD1, he will print word count for RDD1. When you processed RDD2, you know RDD1, 2, 3 are same D stream RDDs. So after RDD2, he will print word count of RDD1 plus RDD2.
Okay.
Then after RDD3, he will print sum of RDD1, RDD2, RDD3.
And RDD1.
So this operation will do pairs dot print. Function is not printing. When you come out of function, then you print. And in this one more point is you have to tell the initial start point because you are taking previous state. So you have to give some initial RDD for it to process. Right now I have given hello world here, simple hello world. Hello 1, world 1, then start ahead. Add everything to this. So these are the only two lines you need to focus in this example. So repartition we did, stateful we did. We will do one transform example. So transform, so what is the use case of transform? Use case of transform is, let's say you are doing some processing on click data. Let's say click data or some page use web log. You are getting a category ID from your logs and you need category name in your reporting. So you have to do join for category ID and category name. But what you are getting as a fact from the data is a string. But your mapping for category ID to category name is a static. That's not a stream. So how will you join a stream with a static data, data at rest? So for that you use this transform operation. In the transform you get a handle for a RDD. Once you have RDD this side and RDD this side, you can use all the operations for RDD. So when you do word count or transform, you get, so this RDD is my variable. So internally they don't give, I can simply say X here and say X here. This is my variable. So I define a variable that give me a handle, name it X, and what operation I am doing is X dot join data. And this data is one file I am reading here. Spark context.txt file, I am reading a data file. So I'll simply read this data file, do a map operation on it and creates a like key value pair out of it. So once you have key value pair, you can do join. So that that operation I have done. If you already have a key value pair file, you simply read it and just use this function. So this is word count or transform x dot join data. If you have filter operation, you can do filter operation. You can do all data cleansing operation here. You can, like, sometimes there is a optimization steps ahead, so you have to do stats collection. So you can do stats collection in this function. So all the ingest operations that you can do, data cleansing, filtering, stats, you will use this kind of operation, and you will put here word count or transform x. And the benefit of this transform is whatever code you have written in your batch, you just simply use that function here. Because in this both are RDDs. You get a handle to RDD, and other operation also you have written on RDDs, so you can use it here. In the case you are on data frames, not on RDD. So you got a handle here x, and this x can be converted into a data frame. So you simply say x dot to data frame and give your schema. You create a data frame. You are from a SQL background, you write SQL query. If you are from a like DSL, you write DSL and then write your code. Same batch code you can exactly copy paste. You don't need to do any special maintenance of the streaming code in this case. So now your example window you asked, window 1. So I can go here and start all the operations actually. So in Spark we have many kind of operations. One is like repartition I explained. Another one is for each RDD. For each RDD you can use, like for each RDD you again gets a handle of x, then you can do. It's like transform and for each are like same. Little difference in there. And these are the all stateless operations that you can do with the dstream object, not RDD. RDD objects functions are enough. These are on dstream, exactly on the dstream. You don't need to go to RDD part. You can say dstream dot map operation. So whatever data you have in dstream for each RDD, for each line, you will do this operation. So map, flat map, filter, repartition, reduce by and group by. These are already predefined functions we have in this on the dstream object. You can directly keep on doing the group by on the dstream. You don't need to write a logic for this on using these APIs. And for stateful operations we have two. One, you maintain a state for a window, or you maintain a state from the beginning. So update state by key I explained. Window I will show you example next. So I came here for this part. So we have window operations. So for window operations we will go a little in theory also. Let's say you have a window. So first constraint on the window is your window interval should be a multiple of batch interval. Because batch interval decides a RDD, and one window can, minimum unit of the window is RDD. Either RDD can be in a window or it will be outside of the window. So you have to define a window into a multiples of batch interval. In this case I have a window which is 3 RDDs. That means 3 times of the batch interval. You won't write 3 here. Batch interval is 10 seconds, you will write 30 seconds here. So you have to maintain that. Now second variable in this is sliding part. So there is a window, how much it will slide. Let's say you can say sliding interval is 30 seconds. That means window is completely jumping to the next 3 RDDs. There is no overlap between windows. If you say sliding interval is 10 seconds, that means every time one RDD will come in, one RDD will go. Because our batch interval is 10 seconds and 10 seconds is equivalent to 1 RDD. Are you following? And then if you go to all window operations, I don't know what is there in PPT, so every time I'm checking it. So these are the all operations that are there provided by the Spark on window operations. You have a window. So if you only use a window operation, from one D stream you will get a new D stream with a window as a batch interval. So your window was, let's say batch interval is 10, window is 30, then you will get a new stream with 30 as a batch interval. Okay, that's a simple window operation. Now we are saying count by window and reduce by window. So in this count by window, they will count all the words or lines inside that window. Those operations in which you don't want to differentiate any, you don't want to do any group by. So you use count by window. But if you want to operate on key value pairs, so reduce by window and count by window, there is a difference. Count by window, you don't care about what type of RDD is. It's a line pair RDD, it's a normal line RDD, or it's a just an RDD or something like that. Whatever RDD you have defined,
take each one of them as
you
one
take
unit.
each one of those one unit and do those operations, count operation or whatever. And reduce by key is restricted for key value pairs, because in reduce you need key value. So when you have key, you do operation on values. For each key you can add, subtract, or you can across keys you use reduce by value. But there are variants of reduce by window and count by window. One is reduce by key and window, one is count by value and window. So when you go to reduce by key and window, that means you are not doing across keys. For a key, do this operation inside that window. Same as count by value and window. As there is no key value pairs in count, so you do only operations on value. Let's say you want to do, you have a line RDD, and there are multiple lines. You count the word and write in front of them. You make a code that take a line, count the words and write line, word count, line, word count, line, word count. Now you want to do count of total words. So simply sum it up the values across the lines. So in that case you will use count by value and window. So this is an example that I have in slide. Oh, join operation. There is join operation also. In this there are two types of join that they provide. One is stream to stream join. So this is very, I found this very useful in streams, because you don't need to write your own logic to do streaming joins. So there is a one stream that you are getting one fun fact, there is another stream you are getting those two fact tables. So you can do stream to stream join. But in this the constraint is, he won't follow the timestamp of the event that at which time it got created. So this is a drawback here, I think. So event creation time is not taken care. He only knows when data came to him. So he will do join on the basis of when data came to him.
So this scenario is about to simplify, there are three streams coming in.
There are two streams coming in, and maybe just say there's an order.
If the streams are delayed, he won't be able to handle it. That's what I'm saying. It's not that based on the time event got created.
Whatever is available in memory.
Whatever available in both the streams RDDs, he will do a join at that point of time.
Then there will also be a scenario where you process this and do it.
That you can do it. That means you are using normal join, which I showed previously, transform operation, that you can do it. There you can use it. There is one more window join. So you can use window join, that only 30 seconds if that data comes in, do a join, otherwise discard it. I don't care about that. Means there is something wrong with the other string. You can specify a window as a half day. If you are assuming you want to handle up to half day delays. That depends on your configurations, how much storage, how much capacity you have. You can extend your use case. Window join is, you have 30-second window in this side, 30-second window in this side. So he will do join across the RDDs within those 30 seconds. So if one stream is delayed by, like say, this stream will rely that there can be a 20-second delay between this. So keep your window as 30 seconds. So somewhere in this you will find a mapping for join, and your join will be passed. That's like you are relying on that it will fall in the 30 seconds. There window join will be helpful. Next is stream to dataset, which I explained earlier. Like one side is a stream, one side is data at rest.
On the window join.
Yeah.
Let's say okay, this is a start and this is a end that I am tracking.
Yes.
So you can do joins between these two.
Yes.
Okay. But if there are misses that I am interested in, is there a way to get in?
If there are misses that you are interested in.
Yeah, so basically everything that comes in, okay, has to go out. Let's say, okay, I'm tracking that.
Yeah, got it.
There is something, okay, which is not processed. Okay, it was not processed.
It's your code, you can do it. You have to just write a filter on the next line. Just say, there is no join, that means there will be a null in that case. Just simply filter the data and pass it as a new stream.
Pass it as a null.
Pass it as a new stream and then do backfill for that stream. You will go to code again. So we'll go to window operation. In this, there are multiple variants of reduce key by window. I have used a variant where I have maximum control. So what I have done in here is, window operation you tell the sliding window size. but you have to tell how to perform the operation when a new RDD comes in and new RDD leaves. Let's say you are doing word count. A new RDD came. So word count is simple plus and minus operation. You have to tell him how to operate on new RDD, because you have to tell that new RDD comes and what previous state and this RDD state you have to append. If one RDD is leaving from the back, you have to tell subtract this RDD word count. Then only you will get correct word count for that window. So in this case, plus and minus is simple. But if you are doing distinct or you are doing any operation of transform, then you have to tell explicitly, and these operations are mandatory to be associative. Otherwise, you can say simply discard if they are not associative. In the minus, you have to say you have to leave with that data. Otherwise, so these all the operations that you do in reduce by key must be associative. And this is our window size. This is sliding window size. There is not even a single change except this function in this and the batch code. Just one function you have to write for window operations. So I have prepared the socket examples. Those who have not downloaded the Kafka, they can run the socket. To run this, you can simply go and in the shell you can say nc-l and code you can change based on your, and then it will be a socket stream and you can use all these code examples. Same examples I have replicated for Kafka also. So if you are interested in Kafka examples, these are same copy of the socket examples. There is one more Twitter stream. So I prepared Twitter stream just to tell that if Kafka is not there, if socket is not there, what to be done. What will be the change when you move from socket to Kafka or Twitter or Flume or any other? Then my keys are okay. I will delete this app. So there is a consumer key, consumer secret, access token, and these 4 variables you need to connect to Twitter. Then I am saying where is that? Twitter utils. So Spark provides different connectors for all these layers. For Twitter there is a connector, for Spark there is Kafka there is a connector, for Flume there is a connector, for RabbitMQ there is a connector. So you don't need to write the boilerplate code. They have already the wrappers. Use those wrappers and create stream function. Pass the streaming context. No need to do any other thing. Just use this Twitter utils, and you have to configuration builder. So in this object, ultimately you will get. So what happened with this Twitter utils.create stream is you got connected to Twitter, you got authenticated there, and you are getting data. So the sample API they have used there is a whatever the sample tweets API you use, that API is behind this, and you will get a stream out of it. Now you use this stream and do operations. So for the demo purpose, what I have done, I have taken a stream. I did a flat map operation on that stream and extracted only the text part of the complete JSON of the Twitter. So complete JSON, I only took the text column. Within text column, I am splitting on space. There is a huge code in this one line. What I am doing is taking the JSON, complete JSON from Twitter, extracting one column out of it, which is a text column, splitting it on space, and keeping only those which contains hash. Okay, because I want to see popular hashtags in last 30 seconds. So I am getting a Twitter JSON, splitting only the text column, split that text based on space, and filter only for hash. Now you have hashtags stream. Now on this
even in 30 seconds there will be multiple JSONs coming, right?
Yes.
So it will consider it.
All these operations are on RDD. RDD is a collection of data. That means whatever came in that RDD he will do for each. Okay. So now we have hashtag stream. In that hashtag stream, what I am doing, again some block of code. In this I am using reduce by key and window. I will summarize it slowly. Like I got hashtags. I put 111 in front of them as word count. Then I did a reduce by key and window. I get word count. This is simple word count here. When I have word count, I am doing one more operation here. Now word and count is there. I am switching it. Count and word. Because I want to do sorting on the count. So in this line I am switching topic count to count and topic. Okay. At next line I am doing sort by key. Now because count is my key, I am sorting on the key, and then I am saying RDD dot take 10. Only take top 10 from the RDD. Why I cannot do this operation, take 10 here, and why I have to write another code? Because I don't have a RDD handle on top of it. Previous one I only operate on lines. For each line I can do anything. So for RDD I have to come to for each RDD. Then I am using take 10. Okay. So when I got take 10, I have top list within that 60 seconds, and I am printing that list. And while printing, I am again reversing it. Give me tag and count, not count and tag.
So when we are writing this output, suppose every 30 seconds, right? So every time different folder is created.
Every time different folder is created.
Every operation, if I am writing it every 30 seconds,
whatever RDD used to do, they will do the same. So if RDD writes a separate file, here they will write separate file. They dump RDD, they don't do any merge or collapse or everything. Because the same data what you are dumping, somebody else has to read it for some processing. So RDD goes into a file, file goes into a file like that. So similar way they will keep it. Unless you are explicitly writing to Parquet or something, they will do optimizations on based on that. Otherwise, this is simply whatever RDD follows. So where I was? Oh, we completed this example. You have to run this. I hope I get good tags. So this way we are getting total. I got 20 events in this time 32 events. So if you say I am printing total events, 41 events within the 30 seconds, and these are the hashtags and these are the counts for this. How many tweets had these hashtags? Better to stop it. I don't know what hashtag become. Okay, so now we will go to task type. So I will go to Kafka. So in Kafka, if we start a Kafka, we will start Kafka broker. We will start Zookeeper first. Then we will. I can do the example.
So can you just say one thing?
Yeah.
When do you want to use the brokers?
Brokers.
Rather than using the Zookeeper, I see some scenarios where people using brokers.
Broker is different. Zookeeper is different.
No, I'm saying what are the scenarios when you should use them?
You have to use both.
So if you just connect to Zookeeper.
No, so Zookeeper and broker, like you have a master. Zookeeper is you to tell that there is a master here.
Correct.
Zookeeper is not a master. Master has to do master operations. Zookeeper is just coordination.
Yeah, but it's going to give you the leader by itself actually, where you want to connect, right?
Yes. Let's say, okay.
So what I'm saying is, okay, maybe I'm mixing it with a little storm here.
Okay, maybe.
Because
So
there you have a concept of talking to static host or talking to Zookeeper directly.
No. This is not the same. So even if you are talking to a Zookeeper is not giving you data. Zookeeper will tell go there and take the data.
Correct.
Same here. You need a broker. You go to Zookeeper and say where is your broker. Then Zookeeper will give you the broker address. You connect to the broker and get the data. You need both broker and Zookeeper. You cannot say either I use Zookeeper, either use broker.
Okay.
So I can start all these processes. So I am starting Zookeeper. I hope I don't have previous data in Kafka. So I started a Kafka server participant. I am starting second server. 3 brokers I started. I wanted to use partition 3, so I created 3 brokers. Let's see, I have test already. Test 1 is already created. No need to create it. And this is my office. So now we have Kafka brokers up and running, Zookeeper up and running. Now I need a producer who will produce data for us. So I have Twitter Kafka producer. Again, we'll use Twitter. We'll get the tweets and push the tweets to the Kafka. So I am pushing the data here to Kafka. And I'll check ports are same. 9 909094 and test 1. So test 1 is topic. These are list of my brokers. Okay, this is good. So this code I am not going through. This code is almost the same which we did in Twitter. So there I have added one simple more function for Kafka. This I am creating a listener. These are other helping functions for Kafka, and I am using this line producer.send data to send the data to producer broker. Now we start this. So zookeeper is running, broker is running, producer is started now, and every tweet I am replicating 2000 times so that I get something. If you go to direct Kafka, so direct Kafka we connect directly to brokers. So if we have 3 brokers, we have to give 3 IDs there. So we have to, in this case we don't connect to zookeeper. Direct Kafka we directly go to broker. From this broker, whatever partition you are holding for this topic, give me the data. That way it will go. So we have a topic test 1. For this I am created 3 partitions or 4 partitions I have. So for each broker you will say this partition offset. So I should start this, then we will discuss. There is a huge pile of data in Kafka now. So as we are replicating each tweet to 1000 times, we almost get every tweet count above 1000. So now if I kill this Twitter Kafka producer also, because we have enough data in producer Kafka, it will keep on. Direct Kafka will keep on reading from Kafka and moving ahead. Oh shit, I started it. This will keep on going until the Kafka says okay, no more data. Then also you will keep on running, that Kafka will give me data, but you will keep on running. It will wait for my termination. Okay, let's stop this and we'll go to the code now. So this is for the confidence that what I have done is working. Rest is there. So what we do, we tell list of brokers and we tell their topics. These 2 are the parameters for direct Kafka API. We say Kafka utils dot create direct stream. So there are 2 functions in this Kafka utils. One is create direct stream, one is create RDD. So the create RDD is used for batch processing. You don't want to do stream, use create direct RDD. Simply get RDDs and then do all the processing. If you want to do stream, use create direct stream. So this updated direct Kafka is both for stream and direct. You tell what is your encoders and this. Main parameters is Kafka params. In Kafka params we are adding broker list and the topic. Topic we are assuming that we will give comma separated list of topics. In broker we will give array, and in that case we will get passages from it, and this code is same. Just a copy paste from there, no change. So only change is this one function for a developer to write, and for Kafka what it changed is, let's say how it will work. So we have driver, we have executor. So we will give driver like 30 seconds as a batch interval. So every 30 seconds he will ask Kafka what is the current offset. Initial offset you will tell either min or max. Whatever is the maximum you will go from there, or your minimum whatever you following from the Kafka side. If you are going 0 to that side, you say minimum is 0. So driver have 0. Now your batch interval is 30 seconds. So at 30 seconds there is a compute function which keep on running. Every 30 seconds that compute function will invoke and run. He will ask Kafka what is your offset. Kafka said offset is 0. That means there is no data in the Kafka. So 0 to 0, one range, he will use it as a one batch. One offsets. Driver will work only on offsets. He won't pull the data. He says 0 to 0 stream. checkpoint, pass it to executor. Next 30 seconds, Kafka had a huge data, so he will say 0 to 1000 offset is there. So 0 to 1000, he will divide for batch intervals. For batch intervals, whatever was the offset, let's say batch interval offset was 100, 200, 500, 700. So he will create a batches of 0 to 100, 100 to 200, 200 to 700, 700 to 800. Because that time, in that interval, there was huge events that he coded from Kafka. So there will be these batches. These batches will be passed to executors. Executor will go to Kafka. This executor say, I got 0 to 100. So he will go to Kafka, give me 0 to 100. He will take it and process it. So there is no receiver. Driver only got the offsets. He passed the offsets to executor. Executor only executed for that offset. Checkpointing is only done for offsets, not the data. So there is no data replication, there is no receiver failover conditions. I am done. Any questions?
Thanks, Sachin. Hey guys, thanks for coming over. As usual, we want to get your feedback every time we spend some time. You guys want to change the style of doing it, any feedback every time we ask. So we try to customize to see if it is possible. So if you guys have any feedback, please do share.
One feedback is this time the timing was perfect because for past meetups we are overrunning, but this time it was just perfect.
Correct. Actually, that was a very strong feedback. So we tried hard to finish within 1.5 hours or something. We still overshot maybe a little minute, few minutes here and there, but
that's why we postponed the performance to next meetup.
Correct. So the next one, we want to pick up actually industry use cases, which is really what you guys face there. The next one, we want to spend a lot of time on the performance tuning on Spark streaming alone. Because we are facing a lot of problems when we are fine tuning it. So we'll come and show you what are the different things we adopted. And we'd like to hear your opinion also. If you guys have any inputs to share, when you did streaming, how did you optimize? We are happy to hear. And if you guys have any use cases you're already working and you want to share here, feel free. We will give you a stage and you can share your experience. Because we are interested to see what are the different use cases you guys share.
Can we have any discussion on the real-time processing when we say we always have this contender like Spark streaming and Spark, right? So if there can be one discussion on that, based on that,
which one to pick it up?
Yeah, in what scenario? So like comparison if possible.
Comparison session. Okay, so I thought we did today. Maybe we didn't do the justice, I think.
I'll add one more thing actually there is. I'm not comparing Apache Flink here actually.
We can do that.
Okay, that's a good one.
We can do that. We have thought of it.
Yeah, because I see that's getting a lot of.
Yes. So
I think Madhukar wrote on blog also, right? On Apache Flink compare. So there is one good blog. You should read it. So
there is a small blog.
Madhukar, why don't you start?
Yeah. So
get you this one.
my name is Madhukar. And there was so many people. Come here.
Okay, I try to make a point not to talk in other meetups mostly because I do